In this video, we're going to see how to calculate vertical stress in onshore and offshore conditions. So I'm going to go into my notes and go into chapter number 2, and we're going to start with the lithostatic gradient. First of all, I guess you are all familiar with the concept of stress. Stress is a force divided by an area. So it has the units of force by unit of area, and commonly those are referred in international units as pascals, and in geomechanics as a megapascal, and in field units as psi, pound per square inch. The concept of stress, it's linked, as we were saying, to a force divided a unit of area, and when we apply this concept to stress equilibrium, we can obtain the equations that allow us to calculate the variations of vertical stress with depth. So let's see how that works. In this example, I have a cube which has a weight that is equal to the mass density of the entire rock, including the minerals and the fluids, times the volume times the constant of gravity. In order for that weight to be balanced with the top face and the bottom face of the cube, there has to be a gradient of stress that counteracts that weight. So imagine that this piece of cube is in actually in a space, three-dimensional space, where I have more cubes below this particular cube and also on top. Then the stress on the top face and the bottom face is going to depend on the stresses of the adjacent blocks. So the stress on the top face is going to be SV, and the force is going to be SV times the area. The stress on the bottom face is going to be SV times the area plus the additional stress which is needed to counterbalance this weight. All right, so let's work with this equation, and let's see what we get. We're particularly interested on this additional stress which is needed to counterbalance the weight. So if we put this into equations, all the stresses which are in this case going down are going to be vertical stress on the top face times the area times the weight of this cube, and that has to be counterbalanced by the stress on the bottom face plus this additional stress times the area. Notice that the area of the top face and the bottom face is equal to delta x times delta y. And when I apply that, I replace A for delta x and delta y. I can also realize that these two factors are the same, SVA, so they are going to cancel out. And also, if I consider that the volume of this cube is delta x, delta y, delta c, then I obtain this equation 2.3. And if I divide now all of that equation by delta x, delta y, delta z, which is the volume, I obtain that the variation of stress SV with depth delta z is equal to the density of the rock, the mass density of the rock, times the constant of gravity. And this is basically telling us that all the additional weight that, or the additional stress that I get as I go deeper and deeper is equal to the weight on top of each layer, which is proportional to the density of the rock and proportional to gravity. This term that we see over here, delta SV divided delta Z is what is called a lithostatic gradient. It's also called the gradient of total vertical stress. All right, let's see what else we can do with this equation. The gradient of stress, which we can express it in terms of infinitesimal variations. Let me write it over here. We can write it as dsv divided by dc can be integrated into the equation that you see here on the bottom on the 2.5. So if I move dz to the other term on the other side of the equal sign, and that multiplied the mass density times g, if I integrate this equation, I can obtain what is the absolute stress at the given depth. This integral is very easy. So the integral of the differential of SV is just going to be SV. I'm going to further assume that the stress on the free surface is equal to 0. So this is our free surface, which is a ground surface in an onshore case. And if I were to consider that the mass density of all of these blocks here is the same, then the integral of differential of z is just z going from 0 to depth z. And therefore, the equation simplifies to vertical stress being the product of mass density of the rock, including everything, minerals, water, everything, times the constant of gravity times depth. So let's see what this gradient and what these stresses look like for typical conditions. So let's assume that we have a rock made 100% of quartz, so all the solid part is quartz, and it has a 20% porosity filled with water. All right, the first thing that we're going to do here is to calculate what is the bulk density. And as we were saying before, this is the density of the rock, including everything, minerals, water, gas, anything that could be in there. And that equation is very simple. You can see it over here. Is what is called a weighted average. Is the proportion of the rock, which is the mineral part times the density of the mineral, times the proportion of the rock, which is pores, and it's filled with water. It's just a linear volume average. Let's further assume that the density of quartz is 2,650 kilograms per meter square, and the density of water is 1,000 kilograms per meter square. And knowing that the porosity is 20%, this equation leads to a bulk density of 2,320 kilograms per meter square for this particular rock. So if you had another rock, for example, a carbonate, what you will have to do is to look for the density of that mineral. For example, in this tab, I have opened a database that tells me what is the specific gravity of quartz. That is the mass density of the mineral divided the mass density of water. And it's 2.65. That's why I have here 2,650 kilograms per meter square. For example, for the fluid part, if you have your rock filled with gas instead of water, then for the density of the fluid part, you should replace this for the density of that particular fluid, let's say gas, 100 kilograms per meter square. All right, now that we have the bulk mass density, if we want to obtain the gradient, which is what I am being asked over here, I need to multiply that times the constant of gravity, all right? And let me jump over here. In the international units, we just multiply times 9.8 meter per second square, and the result of that is going to be 22.7 times 10 to the third power Pascal divided by meters. These units are not very handy to use in geomechanics. So instead of using this Pascal per meter, we use megapascal per kilometer. Why? Because in petroleum engineering we have quite big depths in the order of kilometers, so it's just much easier to use megapascals and for distance to use kilometers. So for this particular rock, if I have a formation which is continuously made of this rock, then every kilometer I would have an increase of 22.7 megapascals. If you want to convert this to field units, what you have to do is to also to work with field units, and in that case, here you have the solution. The density, equivalent density of that rock, here is the explanation of how to do that. But if we just go to that value, it will be 144.8 pounds force per feet cube, and this one is already considering gravity. That's why it has the force over there. The only thing I have to do in order to convert it to psi per foot is to convert this pound force per square foot to pound force per square inch. And when you do that, you're gonna find out that the result is 144.8 divided the square of 12, which is 144, and is very close to 1. All right, so this always raises some issues related to when do I put G and when I do not put G calculating the gradient. So when you are working on the metric system, not metric, you should have your bulk mass density in metric units multiplied times G, okay? When you are working with metric units. If you're working in English field units, you don't have to multiply times G because the G is already accounted for in the term pound force. All right. So, for example, you could have a rock which weighs 144.8 pounds of mass. If you want to convert that to force, the only thing you have to do is just to call it that's a force, and that's all what you have to do. So in this case, what you're going to have is to use the density in English units, but this one already accounts for G, and this is going to be in the term or in the units of pounds force, in this case per inch square, times or by unit of length, and this is going to be a psi times foot. Okay, so this might be a little bit confusing, but remember that it's always easier to work with metric units when you are doing unit conversion and then to pass that to field units. But if you don't want to go work in field units, remember that in order to calculate these gradients, you do not have to multiply times 9.8 because 9.8 is just for the metric units. Gravity or weight is already accounted for in the pound force term. All right. Then with this problem, we have seen that in typical onshore conditions, this value is about 23 MPa per kilometer or 1 psi per foot. And this number, particularly this one, is very easy to remember. And I'm going to ask you to remember this number, okay? Every foot, we have an increase of 1 psi in the total vertical stress. And probably you can compare that to values that you already know. Like, for example, what is the gradient for hydrostatic pore pressure? Do you remember that value? That is, let me write it over here, the variation of pore pressure with depth or hydrostatic gradient is, under hydrostatic conditions, 0.44 psi per foot. And so we can see now that the lithostatic gradient or vertical stress gradient is about twice, a little bit more than the hydrostatic pore pressure gradient. All right, so let's see two short examples about how to calculate vertical stress onshore, and the second one is going to be how to calculate vertical stress in offshore condition. It's not the same. For onshore condition, it's pretty straightforward if we consider that the density is constant. So if the density is constant, and also if we assume hydrostatic pore pressure, then pore pressure is just going to be equal to the density of water times G times depth, and vertical stress is just going to be the density of rock with everything in it times G times Z. And this is going to be the result. At a given depth, if we consider that the density of water is constant, and this is hydraulically communicated with the surface, which means it's under hydrostatic conditions, and if the density of the rock is also constant, then as depth increases, both pore pressure and vertical stress, total vertical stress, are going to increase linearly. There is one more thing to observe in this example, and it is the difference between total vertical stress and pore pressure. That's what is called effective vertical stress, and is denoted with the letter sigma. We're going to see that this is quite important later on, because this effective stress is actually what is holding the rocks together. Not that much the pore pressure, but the effective vertical stress. Under larger the effective stress, the more compaction we're going to see in rocks. This is going to be a little bit more evident when I explain the offshore case. But for the onshore case then, we have that, let me see if I have the equations over here. No, not right here, but the equations for this are going to be simply pore pressure equal to density of water times G times C, and vertical stress is going to be, let me write it over here, is going to be just the density of the rock with everything in it, the bulk density, times G times Z. For example, if I were at the depth of 10,000 feet, then vertical stress would be 10,000 psi, and the pore pressure, if it is under hydrostatic condition, would be 4,400 psi. It's as simple as that. All right, let's see now what we will see in offshore conditions. I'll come back to this example later on. Actually, I'm going to send you a package of coffee in the home kit that we're working on and putting together and sending it to you. Okay, so let me jump here. You have an example about how to calculate these stresses and pore pressure in a given location. The same equations that we have been using so far. And let's jump to the offshore case. In offshore conditions, even though if the rock is made out of the same material, in offshore conditions, I'm going to have a column of water which is on top of the the ground surface or the sea bottom. All right. So in that case, I'm not going to be able to assume that the density of everything on top of my point is the same, because the density of the water is not going to be the same as the density of the rock. So in that particular case, what I have to do is I have to separate the domain in two: the depth, which is filled with water with its own density, and the depth from the bottom of the ocean, from the mud line, to the particular depth that I'm considering. And in that case, the vertical stress is going to be the summation of the column of water, which is the density of the water times gravity times the depth of the water, and that just accounts for the weight of the water on top, plus the weight of the rock on top of the point I'm looking at. And it's just the weight of the rock, okay? I already counted for the weight of the water. So in that case, I have to multiply the density of the rock, if it's constant, as shown in this case, uh, in, uh, in the entire rock, times the difference between the true vertical depth from the water level to the point minus the depth of the water, and I add all of these together, and that's going to give me the total vertical stress. Let's assume for a minute that I am under hydrostatic pore pressure conditions. Then the pore pressure at this particular place, if it's under hydrostatic conditions with the pores connected to the free surface of the water over here, then the pore pressure is just going to be simply the density of the water times the total depth from um, the level of the water here on top. So just density of the water times G times Z. And that's why this follows a nice linear relationship. All right, same as before, the difference between the total vertical stress and the pore pressure is what we call effective vertical stress. And as I was telling before, this is what holds the rock together. This is what actually compresses the rock and reduces porosity as a function of depth. So my question here is, try to imagine if you were to dive out of this boat, go to the bottom of the ocean and try to grab some sand, which is over here at uh, at uh, at the bottom of the ocean. The question is, would that sand be strongly attached to the ground because I have a high vertical stress? Notice the vertical stress is not zero at that point. Or it would be easy to remove and easy to dig in this region? Okay, the answer to that question comes or is related to the effective vertical stress. Actually, here at the bottom of the ocean, the vertical stress is going to be zero. This is the difference between the total vertical stress and the pore pressure. And what that means is that there is nothing holding that sand attached to the bottom of the ocean. It's just when I go deeper and deeper that the weight of the rock is starting to add in stress on the rock and is holding the rock together. But here at the bottom of the ocean, there is nothing holding it. And at that point, that effective stress is equal to zero, even though the total vertical stress is not equal to zero. So let's see a proof of what we were just saying before, and I have a video here to share with you. This is a video of an octopus that it's at the bottom of a sea somewhere, and you see at some moment it starts to push water into the sand, and suddenly it's going to disappear. All right, so you could do the same if you were able to do like the octopus to expel a jet of water into the sand. But the main idea here is that no matter what the depth is, the effective stress at the bottom of the ocean is going to be zero. It's just when you go below this depth that the effective stress is going to increase. All right, so here you have the rest of the equations and also an exercise to compute pore pressure and stress in offshore conditions. There is one more thing I would like to share with you in this video, and is this example here, which is at the bottom, which is a calculator of pore pressure and vertical stress for, wait, I need to run this again, which is going to allow us to calculate vertical stress and pore pressure, assuming that the density of the rock and the density of the water are constant, and also is going to assume hydrostatic pore pressure. So you can use this code for your homework, okay? And I recommend to write your own, okay? But you can base your homework based on this. I actually put this in here to share it with all of you. Your homework is going to be more complicated though, but you can find some inspiration in this Python code in order to solve your own. So let's just give it a few more seconds, and this is going to be ready. There we go. Let me run all of this. And here we have the code. And what this is doing, it's calculating vertical stress and pore pressure with a given depth for the seafloor. And for example, if I increase the depth of the seafloor to, let's say, 1,000 feet, so now you see that the vertical stress is not starting at zero anymore. Now at the seafloor, it has a characteristic value, and the pore pressure increases linearly, vertical stress increases linearly. Let's go a little bit more. Let's go to, let's say, 2,000. Oh, let me leave it there. 3,700. I have the vertical stress. I have the pore pressure. What I'm going to do now is I'm going to change, for example, the gradient of pore pressure. If this is not under hydrostatic conditions, we're going to see later on that this gradient of pore pressure could be higher than 0.44. And many times what it happens in reality is that very close to the seafloor, the gradient is close to hydrostatic. But as we get deeper and deeper, the gradient is going to change. So if, for example, the rock would be a little bit heavier, then this one will be a little bit higher, and the vertical stress would increase. And remember that the difference between the total vertical stress SV and the pore pressure is the effective stress. If we had a pore pressure which is higher, as in this case, you can observe that the effective stress is going to get smaller and smaller. Okay, so this is the end of this part. In the following section, we're going to see how to apply the general method to calculate vertical stress for a real wellbore.